Let's take a look at example 2. Determine the size of the monthly payment required for a loan of $100,000 at 9% compounded monthly if it is amortized over 25 years. Also, we'd like to determine the number of payments that are required to pay off the same loan if the payments are increased to $1,600 per month. Let's start with the time diagram. We have a loan of $100,000. That means that we've borrowed the money today, $100,000 today. Oh, that's the present value, so that would be 0. And we've got 20 monthly payments at 9% compounded monthly over 25 years. That's 12 times 25, or 300 monthly payments. So we've got 1, 2, all the way up to 300 monthly payments of our dollars at the end of every month for 25 years. And so in this particular case, we're asked to determine initially the size of the monthly payment that is required for this loan. What formula do you think we're going to use? Obviously, we're going to be using the present value. So we're going to use the present value formula to determine the size of the monthly payment. We know that the interest rate is 9% compounded monthly. So that's 0.09 divided by 12, or an I value of 0.0075 per month. So using the present value formula, we've got present value of $100,000 is equal to our dollars per month multiplied by the present value factor, because we're using the present value formula. So that would be 1 minus 1.0075 negative 300, because there's 300 monthly payments of our dollars, divided by 0.0075. So you work out what this annuity factor is, store it in your calculator, store it in memory 1, divide it into $100,000, and you will end up with a monthly payment of $839.20 per month. Now, we've determined that the monthly payment for a 25-year term is $839.20. Now, what would happen to the term or the period of this loan if the monthly payment is increased to $1,600 per month? In other words, what happens to the length of the amortization period if the payment is almost doubled? Let's take a look and see. So now we have the same loan. In other words, the loan is still $100,000, so the present value is still $100,000, and we'll put that at the beginning of our time diagram. But now we are making monthly payments of $1,600 per month instead of $839 per month. So we've got $1,600 per month, and the question is, how many payments are required? So what is n equal to if our monthly payment is increased to $1,600? So I'm going to show an annuity here of the payment size is $1,600, and the same interest rate, still 0.0075 or 9% compounded monthly. The question is, how many payments are needed? Well, where's our focal date? Our focal date is, again, back at the present value date. So we'll use this as the focal date, and that means that we're going to be using the present value formula. That $100,000 represents the present value. So we're going to start off with the present value formula, which is going to tell us that $100,000 is equal to $1,600 per month multiplied by the discount factor for annuities. 1 minus 1.0075 negative n exponent, n is the number of payments, divided by 0.0075. So let's attack this equation one step at a time. What are we going to do first? First of all, we'll divide both sides by 1,600. So we've got $100,000 divided by $1,600 is equal to the annuity factor, 1 minus 1.0075 to the negative n exponent divided by 0.0075. Well, 100,000 divided by 1,600 works out to a value of 62.5. So 62.5 is equal to the annuity factor, 1 minus 1.0075 negative n divided by 0.0075. Now let's see for a moment if we can figure out what this significance is of the 62.5. What does that mean, or what is it telling us? We've taken $100,000 and we've divided it by $1,600. What this tells us is that if the interest rate was 0, there was no interest at all, and there was no discounting at all, it would take us 62 payments to pay off this loan. In other words, at a 0% interest rate, it would require 62 payments of $1,600 to pay back the $100,000. Well, there is an interest rate, and the interest rate that's being charged is 9% compounded monthly. So what does that tell you about N, the number of payments? The number of payments, because I have to pay interest on top of that, is going to be much greater than 62.5. I'm certainly going to need more than 62.5 payments if I will be owing interest on that $100,000 loan. So I know that the number of payments will be greater than 62.5 payments for sure. Well, let's carry on now, solving for N. Next step is we're going to multiply both sides by the 0.0075. So multiply 62.5 by 0.0075, and you'll end up with 0.46875. And that will equal to the numerator of our annuity factor, which is 1 minus 1.0075 to the negative n exponent. Now, the next step is to isolate the term containing the n, and so we're going to do that by subtracting 1 from both sides, so minus 1 from both sides, and we'll end up with 0.46875 less the 1, or negative 0.53125 is equal to negative 1.0075 raised to the exponent negative n. Now we've got a double negative here. A negative on the left side equals to a negative on the right side. So what we should do is definitely multiply both sides by -1, or change the signs to positive, because you can't involve logs with negative bases. So we will have 0.53125 is equal to positive 1.0075 to the negative n exponent. The exponent still remains as negative. Now we're ready to log both sides, or ln both sides, and we'll end up with an equation that says ln of 0.53125 is equal to minus n times the ln of 1.0075, or in other words, minus n is equal to the ln of 0.53125 divided by the ln of 1.0075. And working this out on your calculator, you'll end up with a value for negative n is equal to negative 84.65. Well, again, a double negative means that positive n is equal to positive 84.65. So what is this telling you? This is telling you that we need 84 full payments of $1,600 per month, and we'll need an 85th smaller payment, or an 85th payment that is smaller than $1,600. And what this means is that you've gone from a 25-year amortization period, or 300 monthly payments, to 84 monthly payments plus a smaller one. Now 84 monthly payments is 84 divided by 12, or exactly 7 years. So that's going to require 7 years plus 1 extra month for the 85th payment. So you've gone from a 25-year amortization period to a 7-year amortization period simply by increasing the monthly payment.